Good evening, sir.
Good evening. And thanks for starting the session. I was in another session.
Yeah, I understand. I realized, so which is why I started this. Yeah.
Yeah. So I was chairing that session, and that just now it got over.
Yeah. Hello. Best of luck for the rest of your session.
Yeah, thank you.
I'm actually managing a few other things, so I'll just stay
Yeah, sure,
muted.
no problem. I will take care of it.
So,
Yeah.
would you be calling the other attendees, the speakers?
Okay, so let me check who is the speaker for this.
Okay. Let me see if I can help you with that. Yeah, you should be joined with Sridhar Kumar Narsimhan and Nirav Bhatt.
So I think this will be Neerab Bhatt, right? Because Shankar Narasimha is in the other tutorial, I think.
Is he?
Yeah, because in the program I can see Nirav Bhatt.
No, not Shankar Narsimham. This is Sridhar Kumar Narsimham. Both
Okay,
of
okay,
them are the same surname, but this is Sridhar Kumar.
okay, okay.
What I will do you have the phone number of Nirav Bhatt?
No, I don't have.
Okay, I'm sending you one and I will take one. Let's call each of them.
Okay,
I'm
okay.
sending you a chat now. I'll send you Nirav Bhatt's number 8939576 147. This is Mr. Nirav Bhatt, and I'm calling Sridhar Kumar.
Okay, okay. I will call him.
Good evening, sir. I'm calling from ICC. You will be joining the session WETB T5. Okay, it's going to start in the next 6 minutes, sir. If you can join in soon. Thank you.
Good evening, Professor Narasimhan. Good evening.
Okay, I was able to talk to him. He should join soon.
Yeah, so I just called him. He will be joining in 2 minutes.
So same with me. He would also be joining in a few minutes. So I think we're good.
Yes. So he told that maybe I think Mr. Sridhar is supposed to start, I think. That's what he said.
Yes, you are just a Zoom host right now.
Yeah.
like all of us.
Yeah. No, I think two of them are there. No? So I thought that who will start first?
Yes, yeah. So the starting person is Sridhara Kumar.
Okay. Yeah. So he will join.
Have a nice session. Yeah, thank you.
Good evening. We will just wait.
It is 5 o'clock now. I think we can start.
Yeah, I think. Yeah, Sridhar, can we start?
Hope you can all see my screen, and hope it is the full screen. Mira, can you confirm, please?
Yeah, it is full screen, Sridhar.
Hello, this is Sridhar here. I'm joined with my colleague Nirav Bhatt. This is the concluding session, the short tutorial on a priori parameter identifiability in complex reaction networks. Just saving bandwidth, I turn off my video. Just a quick recap. The first day, Nirav covered models of reaction systems and introduced two concepts of identifiability. How do you identify the reaction rates? And second is, how do you identify the parameters in the model? This parameter identifiability was formally defined yesterday. And we started with an example. And formally defined different notions of, different classes of identifiability, globally, locally, and non-identifiable systems. Then we briefly saw how introduced a software, which today Neera will demonstrate. Hopefully everything goes well. DAISY is a software which is built on differential algebra methods to test identifiability. So it could be applied in principle to reaction networks. However, there are even for what we call small reaction networks, there are issues. And we saw some limitations, and we'll also address one other limitation of using standard methods of using differential algebra methods. Standard methods, we'll see how to address them in today's session, the first half of today's session. How do you work with non-rational functions? Just a quick recap. The problem when you want to identify dynamic model from data, the notion of identifiability has three aspects. First is the model identifiability of priori parameter identity, the structural property of the system. It depends only on the model and what measurements you're carrying. You have. You don't work with data as yet. It just asks a very yes/no question: are the parameters identifiable or not? And this is the focus of this tutorial. Second and third are, what kind of inputs have been used for perturbation and what estimation methods. Those are not things which we will cover in this tutorial. So, to put succinctly, the question that you're trying to answer is: does there exist a unique one-to-one map between the model and parameters being identified? Again, quick recap with some laying the groundwork. Consider a nonlinear system with S states, V inputs, R outputs, and P parameters. Assume that they're sufficiently smooth. Of course, this is an assumption that we're going to relax today, but the F and G are rational and polynomial functions. So the differential algebraic methods, again, just a recap of definition. If you give me two realizations of the system in two different parameters, if they yield at least, again, I'm sorry, I should have fixed this, at least different outputs, then it is globally identifiable. If for all finite sets of parameters, all inputs result in the same output, system is only locally identifiable. If for all theta, all inputs result in the same output, the system is unidentifiable. So the differential algebraic approach, basically you try and eliminate in some sense the states from the these two equations and write down only an input-output relationship If necessary, you may have to differentiate the input, output, and so on. You may end up, let's say there are R outputs, you may end up having R, what called characteristic equations, which involves some parameters, inputs, outputs, derivatives of these. And then you collect all the coefficients of these, take these as monomials, the different terms that are appearing, these differential polynomials, and use a randomly chosen value for P. And then you solve the system of equations h of p equal to h of p star and see whether you get unique solutions. If it's unique solution, it is globally identified. If you get multiple solutions locally, if you get infinite number of solutions, it is unidentifiable. So in principle, it works well. In some sense, this is basically doing Gauss elimination. It gives you an upper triangular form where from all these equations, R plus S equations, you eliminated all the states and you got only the R equations involving only the inputs and outputs. There'll be other equations which involve the states and the outputs, inputs, and so on. Those are not, we're not interested in those. So most of these algorithms are guaranteed to converge in finite number of iterations, but what is finite? It could be extremely large. And we saw yesterday that even for very small systems, seemingly small, 2 states, 5 species, 5 measure, or 5 states, 2 measurements. DAISY, so it's a software brought out by colleagues from Italy that doesn't give a conclusive answer. Secondly, it is only specialized to systems which have polynomial or rational nonlinearities. So how do we? This is the for you have large reaction networks, we saw one method of obtaining the input-output map with a very simple linear transformation. And on some conditions, it just comes down to examining rank of a matrix. Well, when you have non-rational non-linearities, then what do we do? So what do we do for non-linear or non-rational when the function and the system is not in the rational or polynomial? So again, just a motivation. Why do we care about non-rational functions? They appear very naturally common. They appear very frequently in reaction systems, especially when the temperature changes. You may have, if you recall from your high school chemistry, typically with every 10 degrees, that's a rule of thumb, it's not necessarily accurate. Every 10 degrees change in temperature, the rate of reaction doubles. So that clearly shows an exponential growth. And that is usually captured where your rate of reaction over here, which we know the rate of the reaction will depend on the concentration and also on the temperature. The temperature dependence, as you can see over here, that's an exponential term, exponential dependence. So let's say there are a single reaction in a constant volume reactor, non-isothermal, so temperatures are changing, but let us assume that there is not change in the densities. It's constant volume. So you write down you have 3 states, A, B, and C. Ca, the concentration of Ca, the concentration of B, and the temperature. You can write down these nonlinear equations, and as you can see, there is this exponential term appearing in all the 3 equations. So there are 3 states and 2 measurements. Let's say you have Ca and T, and 3 parameters: K1, 0. This is usually called the pre-exponential factor. E, which is typically the activation energy, and H1 times K1, 0, which accounts for heat transfer, the heat exchange. The 3 parameters which you need to identify, estimate, and the question is, are these parameters identifiable from the given measurements and the data? Clearly, the differential algebraic approach cannot be used because it's just not, the theory is not set up for handling exponential nonlinearities. So a simple way is to define a new variable called x4, which is e power exponent of minus e by t, and then you add its 4th state, and you can rewrite these equations over here. And x4, you need to have a state equation for evolution of x4, and you get 4 states. So you do, there are again 2 outputs, some concentration and measurement and temperature. You do the same. Now it is the exponential nonlinearity is gone, and you have only rational functions everywhere. So in principle, you should be able to use the standard DAISY kind of approach, differential algebraic approach, and you'll get 2 characteristic equations, A1 and A2, which involve only the inputs and outputs. In this case, there is no exogenous input, so it's only involves the outputs, Y1 and Y2, and maybe the derivatives. So clearly, you can see E and H1 are identifiable, but K10 is not, doesn't even show up in the characteristic equation. So as far as this approach seems to suggest that you cannot identify K10. However, if you could measure X4, then K10 is obviously measurable, because it comes out in the last equation over here. Now, what is X4? X4 itself is e power minus e by t. So obviously, even if you could measure, you can measure temperature, of course, it's a measured quantity, but unless there are 2 ways, it's very this seems to be a very non-physical measurement. Either you estimate, you either measure it or you compute it. If you need to compute it by estimating, by measuring capital T, the temperature, you would still need to know E, which is one of the parameters that you are trying to anyway estimate from data. So how do you get X4? Like secondly, so how do we, in principle, although theoretically you could argue that if you measure X4, K10 is identified, but this is practically infeasible. So now, does this suggest that the system is non-identifiable with these 2 measurements? Actually, no. See, when you work with systems and you work transformations of systems, just a negative result does not mean the original system is non-identifiable. It only means the transformed system is not identified. So you can do a very simple transformation by taking defining z1 equal to log of minus y1 dot minus log of y1. Likewise, z2 is log of y2 dot minus log of y1. And then you take the natural logarithms of both sides in these differential equations. You get z1 is in this form, and you get the characteristic equation. You get z1 can be shown to be in this form. Basically, this is again, you would so in what now I'm doing is you can show that z1 and z2 are in this form. Then if you measure z1, because z1 is just some transformation of nonlinear transformation of measurements, and z2 is also nonlinear transformation of measurements. If you measure z1 and capital T, clearly K10 is measured, can be calculated, E is calculable. In some sense, the simplest way is just to do a regression between z1 and minus 1 by t. So the slope is E and the intercept is log of K10. Likewise, you do another linear regression between z2 and minus 1 by t. Slope you should expect the same slope. And the intercept will be log of minus h1 K10. We already estimated, calculated log of K10 from the first regression. Even though I'm using the word regression here, I'm just using it to as a conceptual tool. As I said, in this analysis, we are still working in a noise-free, uncertainty-free environment. So equivalently, you can think about this is the polynomials in the pseudo-differential polynomials in z1, z2, 1 by y2, 1 by y1, 1 by y2 and y1. So again, what I'm trying to emphasize is a negative result in transformed systems does not mean the original system is not identifiable. Positive result would mean under some conditions that the original system is identifiable because you're having the same parameters. So statistically, of course, the parameter, the statistical properties of the estimators will change and so on, but we are not interested in looking at statistical properties, only looking at answering the simple structural question, are the parameters identifiable or not? And in this case, it turns out that they are indeed identifiable if you are ready to accept and you're creative enough to think of these kinds of transformations. Therefore, the question is, how do you decide these transformations? And if you got a negative result, it does not mean the original system is non-identifiable. So what do we, how is there a way out of this? Now, okay, so maybe I'll just stop here for a couple of minutes and see if there are any questions. Okay, there are no questions. So what is the most, if I have an exponential term over here. So we tried one trick, try to get rid of the non-exponential term, making it a polynomial form of some kind, but that didn't seem to work. At least it gave you a negative result. If it given you a positive result, then we could have been happy. It would have been a happier situation. It's a negative result. So what do we do? So given exponential terms, what is the, as control engineers, what is the most common approximation that you can think of? Not too many people over here. So I mean, I'll just repeat the question. We have exponential terms. As control engineers, how do we handle exponential terms, and how do you approximate time delays in your frequency response analysis? This seems to be fighting.
Paradise approximation.
Pardon?
Yeah, Paradise approximation.
Yes, that's correct. The natural thing is to use Paradise approximation, and it's, of course, when you do that, you end up getting rational. It's a rational approximation, so it can, in principle, if you tried that, it would still fit in your differential algebraic methods. But again, Paradise, when you right, so this is the approximation of order 1 by 1, which means both numerator is an order of approximation 1, but denominator is also 1. So e power minus a is 1 minus a by 2 over 1 plus a by 2. You plug in this approximation over here, you end up getting a rational system. You do your characteristic set A1 and A2. A3 and A4 are basically just saying that Y1 equal to CA and Y2 equal to T. A1, A2 is what we are interested in. So you get everything in terms of the derivatives of y and y dot and so on. So before I proceed any further, just look at what this means is A1 is equal to 0, A2 is equal to 0 are the two input-output relationships. This is not for the original system, but for the approximated system. By looking at this, what do you think? Because I've given the answers over here, but what do you think are the parameters K10, H1, E1, E identifiable? They will be, right? In some sense, if you want to think about it, you do a regression, a linear model between y1 dot, y2, y1 dot, y1, y2, y1, and so on. And you get the coefficients. For the first coefficient of y1 dot will be E, another coefficient of y1, y2 will be K10, and the third coefficient will be K10 times E. The second time also you do a regression between y2 dot, y2, and so on. Basically just trying to use the linear linear model building ideas. You do a kind of a regression. Again, as I said, this is conceptual. You're not going to really, you may not in the end really fit the straight lines between derivatives times y2 and so on. But conceptually, if you did fit a straight line between y2 dot, y2 on one side and the rest on the so-called independent variables, you would get E by 2 as one of the coefficients, H1 K10 with other coefficient. You already got K10 from the previous so-called pseudo regression. So H1 is also calculable or estimable or identifiable. In the differential algebraic setting, what this would mean is you collect all the coefficients of your input-output relations. The coefficients are e by 2, k10 minus k10 e by 2, h times k10 minus h1 times k10. So you just take any random values of in e, k, and h, k10 and e, h, and you plug this, you get these nonlinear equations. And it turns out you have this nonlinear equation. So E equal to 1, K10 equal to K10, E equal to 2, and so on. So obviously this has only a unique solution over here. Because E equal to 1, and from this you can get K10, put it over here, you'll get H1, and you'll get the same value of H1 in the second E. So there's only finite number of, it's only a unique solution, and for this system is globally identified. So what this shows is that the approximated model is globally identified. Now, this is with approximation, right? Now, I decided to stick to a single first order approximation. I decided to stick to first order approximation. What would happen if I wanted to, I decided that first order approximation is not really good enough. I want to do a second order approximation. So you can, there's nothing preventing you, second order approximation of this kind. You will still get a rational system. And then you will get a slightly more complex system of equations. The degree of your terms and their characteristic equation will change. In this case also, you get that the parameters are uniquely identified. There's a unique solution. The nonlinear equations that you get from the so-called exhaustive summary or the characteristic set as a unique solution. So this approximate system is also identified. So what should you do? Should you go on to the third order approximation, fourth order, and so on? Do we stop? Can we need to keep on going ad infinitum? No. What we have shown is you don't really need to do this. You don't really need to keep going on and on. For certain systems where the non-rational functions have two components, a rational part and a non-rational part, which is multiplying like this. If you did an Apade approximation, then if for some order, qth order approximation, the system is identifiable, then higher order approximations will also be identified. And it's not too difficult to see that, because what you will get is, what is happening is these coefficients are really getting, not the coefficients of the Pade approximation, but the coefficients that you see in your characteristic set. Some of them are going to get borrowed from the earlier one. So if the original system had a unique solution, you're going to have more equations. You think about this over here. Previously also you had some number of equations. You're getting more equations. So if the previous system had unique solution, with more equations and more conditions, you will have to get a unique solution. And that is always a solution because you just put in the values. So that is the basic intuition. So if you compare the system of equations that you have from the previous one, you have only more. And the original system was a unique solution. So having more equations, you're going to get only unique solutions. And that's what we formally proved for a certain class of systems where the nonlinearity or non-rational function appears in this form. So the good news is you don't have to keep on trying out this question of what happens. Is it possible that if the first order approximation is identifiable, is it possible that the second order will not be identifiable, and so on? That you don't need to worry about. We have shown that it is any higher order approximation will also be identifiable. And again, intuitively, you can keep doing this, and therefore, as the order of approximation becomes very large, the system is going to approximate the original system much better and better. And therefore, you should expect that the original system also is identified. So what this allows you to do is, I'm not saying that when you want to do the estimation or the identification, you need to put in the Pade approximation. You could still work with the original system. You could work with the original system if you're ready to do some data processing technique or some identification method which works with the original non-rational functions. It intuitively, if the approximated system which are approximated by Pade approximations or even Taylor series approximation, the original system will be not still identified. And to conclude, and why Pade approximation? Typically, why did we use Pade approximation? Usually better rational approximation than Taylor series approximation of same order. So like the exponent, e power minus theta. If you wanted to approximate it by polynomials, for the same accuracy, it seems to be, there is a kind of feeling. It is proved under some conditions that you can get better approximations using Pade approximations of a lower order. So what we have shown is if the approximated system is identifiable, the higher order approximations will also result in identifiable systems. But again, what has to be noted is it's only a one-way result. If the approximated system is not identifiable, does not mean that the original system is not identifiable. So but at least we give you a positive result. If the approximated system is identifiable, then you can relax in the we can take comfort in the conclusion that the original system is also identified. And with that, I have covered what we wanted to do about identifiability of non-rational systems. If there are any questions or there is some discussion, we can have a short discussion for the next 5 minutes or so before my colleague Nirav takes us on a journey through DAISY. That doesn't seem that there are many questions.
So let me go to the DAISY.
Yes, so let me stop sharing and hand over the next half of the session to my colleague Nirav.
Let me just start with two things. Let's remove all the So today now I'm going to talk about the DAISY software. So far whatever we have discussed is the theoretical aspect of using differential algebraic techniques for identification of systems, a priori identifiability of dynamical systems. And today I'm going to talk about a nice software which has been developed by Professor Maria's group at University of Padova called DAISY. It has been there for last couple of years. And this is a current version which uses a reduced platform. So there are some kind of changes have happened. I don't know what is the reason behind it. Mostly, I think to improve the complex computational symbolic computation using DAISY. And you can actually download DAISY from this website. You just type DAISY University of Padova. This website will come, and you have to register it and download. And there are nice instruction has been given which can be used to actually update the software where you need reduced platform. What I have going to do is I'm going to actually demonstrate this particular software, how you can use that for solving some of the problem related with identifiability. So in DAISY, let me do one thing before I go further. I'm going to solve this particular first problem where there are 3 states, 1 input, and x1, x2, p1, p2, p3, p4, p5, p6, p7 are parameters, and 1 measurement is available to you, which is one of them, either x1, x2, or x3. Let me do first thing, that change this example. Let me show you in how we can do it in DAISY. So remember, in DAISY, it is 2 kind of platform. One is, first you have to define a model file in text.txt in a particular manner. So I'll show you how you can define docs.txt in which manner you have to define. And also, after that, you have to run this docs.txt file using certain commands in a reduced platform. So I have already installed, so you can actually go online. When you download the DAISY, there will be one instruction file which tells you how to actually download the DAISY, how to download, reduce. One of the important aspect is you have to use the whatever reduce platform or version they have actually mentioned. Otherwise, there is some kind of incompatibility problem, and you cannot actually use reduce efficiently to run the DAISY, which was one of the reason I was trying out and could not got the result earlier. Then I realized that this is the issue. So you should keep in this thing in mind. With this, let me stop sharing my slides and share my screen. Okay. So Sridhar, you can see my screen, am I right? My screen is visible?
Yeah. At least for me, maybe one of the other audience.
Reason I have shared the screen with you to just show you reduce. So this is a reduced platform, which actually what you have to do is you have to load DAISY. Somehow I could not manage to clear them, but this will only clear the. It doesn't clear. It's only clear the variables. So this is you have to actually type load DAISY $, and it's since DAISY is already loaded, it will come like this. Before that, I just was trying some of the examples to demonstrate you. What I'll do is I'll start with one example and show you how actually we can go from that example to we'll start with a simple example of unknown one. Yeah, this is the better example. So you can see here that there is a system, which system I have shown you earlier. In DAISY, first you have to, this is the inbuilt example in the DAISY. So here you have to first define B underscore is a vector, is the variable vector. So you have to start with the input, then outputs, then states. So here in our case, if you recall, we have only 3 states, 1 input, and as I told you, 1 output, which is y is equal to either x1, x2, or x3. So you have to define that, and then you have to define unknown parameter vectors, for which you want to run parameter identifiability. So here there are 7 variables. If you can look at it, see that it is visible, correct? You can see the slide as well as.
Yeah, I can see both the screen and the slides.
Yeah. So P1, P2, P3. So there are 7. So I have defined them in 7. Then I have to define number of states. In this case, there are 3 states. 3. Number of inputs. There is only 1 input, which is U, and number of output, which is here in this case is 1. Okay. So you have to be a little careful about defining all these things, because these are very sensitive to whatever information here. So if you do not define underscore it sometime, do not show the results or shows the error. Once you define that, I'm defining the model equation here. First model equation is for x1, which is minus p1 x star plus p2 into x2 plus u. Similarly, second x2 you can define, and similarly third you can define. And the fourth one, you have to define the first output, then second output, and henceforth. So sometimes if you have some numerical value, you can actually add it. Right now I'm not doing it, so I'm keeping it as a flag equal to 1. Keep it. Value of initial condition, here you can also actually define. So here x1 if x2, x3. Once you define this file, you can close it or you can keep it open, not a problem. We'll go to the DAISY. So here reduce you go, and you say in. So in this case, my file is, the name is unknown. I see. Will run. Now, what it will happen is what happens is, you can see I ran the file. We started with is basically it wrote that this is the example, this is the model equation. Then it provides me characteristic set. You see. Remember that, like Sridhar has discussed in the first class, that you get a characteristic set in a particular format where you have some ordering. So here the final characteristic set is this particular part, and there are actually other equations. Which is, this is the final characteristic set, and from which we are going to take only one. We remember that this is the only one which has a input-output relationship. Other might have some states. Let's see. Now, using this, what we are going to do is we are going to collect some of these coefficients of these elements, and then we are going to compute by assigning some parameter value like p1, p2, p3, p4. DAISY did by itself, by the way. I don't need to worry about it, but if you are writing your own code, you can define it after this one, and then it will look at the Grosvenor basis, and based on that, it actually says that this model is non-identifiable. Okay. And it shows you a model parameter solution, and you can see that some of them depends on initial conditions somehow. And that might be the reason that it is not identifiable. So what I'll do is I'll change the initial condition here. So you can see x1, I moved to from variable to some number. And let's see whether it still says the same or it can change the tune. The interesting fact is that if I provide the initial conditions, the model is locally identifiable. Same, see here, model is not locally identifiable. And here, model is locally identifiable. So the initial condition, unknown initial condition plays an important role in many of this identifiability. Now, this is just to demonstrate you how DAISY works. It's very straightforward. Only thing you need to learn how to write a model equation. Now, what we can do is we can do following. I have actually took 2 examples which we have actually discussed during our presentation. So this is the known example which we have discussed. Sridhar has discussed. I have discussed. If you have not recalled it, let me do one thing. Let me take this example. So this is the example. I hope that it is visible. And here in this example, we have a 5 states and 2 reactions, sorry. And we have a 2 output which we are measuring. So here I have defined that y1, y2, x1, x2, x2, x5. So the 2 output I have defined and 5 states. And there are 3 unknown parameters, k1, k2, and k3. So that's also I have defined here. You can see highlighted. I'm highlighting it. Then I provided state 5. There are no input here, so 0. If this is there are input, you can put however many inputs you have, and there are output, which is number of outputs equal to 2. Then I have written this equation in terms of x1 and x2. So CA, CB is here. CA is x1, CB is x2, CC is x3, CD is x4, and C is x5. So accordingly, I have written the equation. You can write in x1, x2, x3, x4, x5 form also, or C1, C2, C3, CD, and C form also. There is no, but I have just kept for the sake of simplicity in terms of x1 and y1. Here, I will do is I'll change the output in terms of x1 and x2, which is my CA and CB. And I assume that the initial conditions are not known. That's not the problem here. And what I'm going to do is I'm going to run this example and see whether the system is identifiable with this example or not. So let's go and check. Oh, sorry. I think I didn't save it. I should save it. So, yeah. So it actually did it. ICC tutorial example with R is equal to 2. This is my equation. It found the characteristic set. There are 2 characteristic set they found. A11 and A22 are the characteristics. remember what is the property of the characteristic? Yeah. But last two looks like characteristics. Oh no, I think first two are characteristics. And then they define parameter value for B. They found out the globular basis and they got the same globular basis. And that's why they said that model is globally identifiable. Okay, so very interesting what we have actually discussed in the class. It's happening. Now what I'm going to do is I'm going to change my output to x3 y1 is equal to x3 and y2 is equal to x4. Now here what I have done is x3 is cc and x4 is cd. So according to theory, if you go back and this is very nicely done. So there are no problem. If you measure cc and cd, your rates are identifiable. So this parameter should be identifiable in reality. And as we say, the reaction rate identifiability is only for this one is not possible, but others are possible. So in principle, this one should also give me the same answer which I got for CA and CB. So what I did is here, I did it, try it. And if you notice, it takes time. In the first two, it did not take at all time. It just by fraction of time, it actually gave us an answer. But in this particular case, it did not give us answer. It is taking time. I don't know whether it will give answer to me or not. When we tried earlier for a couple of earlier version of DAISY, when computation was little more done in a different manner, I think Reduce provides a better way of solving the problem because it is a general tool, but still it is taking time. And I do not want to waste any time. Just my point I wanted to make here is that although with the CC and CD, the system is identifiable, the DAISY is not providing the answer, at least in the last 1 minute which we are looking at it, it is not providing me answer at all. And that's where the bug stops. So can we actually reformulate it, and with the x3 and x4 as my measurement, can I actually show the system is identifiable? So what I'm going to do is I'm going to now break this one, and open another file where I have written a model in terms of extent. So what I have done is I have gone back and wrote a model. You can see x dot is equal to this form, y is equal to this form. Here y can be anything, depending on the what is you are measuring. Here CACB we are measuring, then this is going to be y. So first I'll show with that, and then with the CC and CD, CD as a measurement. So you can start with this. So if you have seen, I have done the same. Now the states are reduced to 2, measurements are same are the parameters. I have written these model equations, which I have described here in terms of first two and the last two are linear equation, affine equation in terms of x1 and x2, which is minus 2x1 minus 2x1 and minus 2x2 minus x2 plus c1 0 and x1 minus 3x2 plus cb 0, right? And we are going to initial condition anyway. Here we know for the x1 and x2 has to be 0, that we know anyway. So I have defined that, and that is that. What I'm going to do is I'm going to run this file. So voila, same tutorial. same example. I got F1, I can see, you can see. Just to, oh, not going beyond certain length. It looks like, no. Anyway, so it doesn't matter. You can see characteristic set is given, parameter value, and it's a globally identifiable. Which are this one. Now let's look at with CC equal to CC and CD as a measurement. And as I told you, when you write CC and CD, the measurement is the N is actually identity. So technically it will be simple. As a matter of fact, it will be X1 plus CC0 and X2 plus CD0. We'll see what it will provide us. Again, it produces results by redefining. Of course, the biggest problem here is you can see the why by redefining our whole model, we can actually get answer without any problem. It's the time it takes. It's very big, very small. I mean, fraction of second it takes to give you answer, and this particular input-output relationship describes that importance of model formulation. When you have a simple model formulation, DAISY could not figure it out the computation very in a straightforward manner. However, by just reformulating with the same measurement, I am getting back my complete complex characteristic equation or my input-output map without much problem. Imagine that if it for a simple system it happens, for a complex system, how much reformulation will be helpful to us. So with this, I would like to conclude our discussion. Let me just give a brief idea about whatever we discussed. We discussed a couple of things. We discussed modeling, we discussed differential algebraic approaches in general, as well as we have discussed how to use DAISY software to solve this problem. So the literature, when many of you have asked for the literature in the last couple of classes, what is the way we can do it is the following, that you actually go through some of this literature for differential algebraic approaches and DAISY related information. So particularly this Belu paper is quite good math paper to understand how DAISY works and some of the nitty-gritty. This one is more mathematically involved, but discuss about role of initial conditions and how identifiability works, more in a theoretical sense and theoretical results. And this publication discusses some comparisons of different parameter identifiability methods available in the literature and their comparison in biological systems. Related to reaction networks, for the modeling of the reaction systems, you can look at one of our old paper in the AICT journal. Then for identifiability in a model with non-rational functions, what Sridhar talked about today is available in this Automatica paper. And some of the work with the Varghese on the complex a priori identifiability, again, Sridhar talked about yesterday, where how you can actually reformulate the model and solve the problem is available in a complex reaction network is available in this paper, in the IFAC paper online. With this, I would like to thank you. And if you have any questions, I can answer. there are no questions, then should we stop the tutorial, or we should terminate the tutorial?
Yes, you can.
Okay, then Shashi Ranjan Kumar, I think Shashi, what
Yeah.
we should do?
Yes, then if there are no questions, then we can close the session.
And then
Okay,
thank you. Thank you, everyone. Sridhar, you want to say?
No, just thank the organizers, the audience, and the student volunteers and friends who for helping us conduct this session.
Yeah, so if any one of you are interested, you can always write to us. We have a small center which actually does a lot of this work. Just you can always get back into touch with us through the center or those aspects. Those who are interested, our center is working on a lot of network systems applications, and one of them is a reaction networks. We are a bunch of faculty from different different department, from chemical engineering, electrical, and biotech. We work with the different aspects. You can get involved. 1 second. Hello. Can I call you in some time? So you can come as a project associate trainee, PhD student, postdoctoral fellow, and you can always write to me or Sridhar, or look at more information on our website. So yeah, anybody is interested, please do contact us. I think with this, I have nothing more to say. Sridhar, so thank you everyone for participating and making it enriching experience. Sridhar, you want to say anything else?
No, that's all. Nothing. Thanks again to everybody.
Yeah, thanks.
Be safe.
Yeah, be safe. Yeah, thanks. Have a nice evening. Bye-bye.
Yeah.
Thanks,
you.
Shashi, for organizing the session.
Thank you.